Hello everyone! In today's video, we are going to go through some basic concepts in organic isomerism, including how to count isomers, priority rules, EZ and RS isomers. So let's begin with a simple question on what is isomerism? Well, isomers or constitution isomers in particular, molecules with the same molecular formula or the number of atoms of each element but different structural formula. So they look different, the two molecules will look different when you draw them out in two dimensions. Meanwhile, stereoisomers or configurational isomers, or people usually call them geometrical isomers as well, are molecules with the same structural formula but different arrangements of atoms in space. So the two molecules will look different when you compare them in three dimensions, even if you rotate any of the single bonds or you rotate the entire molecule. So the two molecules shown here are constitutional isomers. So as you can see, they have the same numbers of carbon, oxygen, as well as hydrogen. However, when you draw them out, they look different in two-dimensional space. So the first one has two carbons together. So the two carbons here are together, while for the second one, the three carbons are together. So obviously the skeletons of these two molecules look different to begin with. On the other hand, stereoisomers may look something like this. So, in a molecule on the left, when we align the two green balls to the page, the red ball is sticking out while the pink ball is pointing into the page. However, you see on the right-hand side, the diagram on the right, the pink and the red ball actually swaps positions. So for these two molecules, no matter how you rotate them in space, they will still look different. And therefore they are stereoisomers. Now, having clarified what are constitutional as well as configurational isomers, let's move on to how to count constitutional isomers. So the first step you need to take is to change the skeletons, including forming rings if possible. And one easy way to do this is you move from the linear to the branched molecule. So the second step is to change the double bond placements in each of the skeleton if there are any double bonds or triple bonds to start with. Then the third step, and finally, you just have to check for duplicates and avoid them. So let's start with a simple example. So C4H8. With four carbons, you can draw these four skeletons that are possible. Then you can move the one double bond in each of the skeletons, keeping in mind the number of hydrogens you have available. So in this case, you have 8 hydrogens available, and you can only have one double bond or one ring. So just make sure you don't have any of the you don't draw any duplicates. So if you draw the double bond here, or if you draw the double bond here, both cases will give you the same molecule. So make sure you don't draw both. Now, you might ask, how do we know how many rings or double bonds we need to draw? Well, we are going to use a concept called degree of unsaturation. So, degree of unsaturation basically, in our case, means the number of rings plus the number of pi bonds. So, for example, if you have a double bond, then you have one pi bond. If you have two double bonds, you have two pi bonds. And if you have a triple bond, you have two pi bonds as well. So how do we derive the degree of unsaturation? Well, the big idea is that you need to take the number of hydrogens in a lookalike saturated molecule without rings minus the number of hydrogens and halogens in this molecule, and you're going to divide it by 2. So why do we do this? Let's demonstrate this with an example. So in this case, this molecule here is saturated. So remember, saturated means there are no double bonds or triple bonds. So it means that a molecule has the maximum number of hydrogen that its skeleton allows it to have. So in this case, the molecule here is considered unsaturated as well as ringed because you have a triple bond, you have many double bonds, and you have a ring. So this is our target molecule, and we're going to count its degree of unsaturation. So while we don't usually call rings unsaturated, we are going to use the degree of unsaturation to account for them because their effect upon the formula of the molecule remains the same as a double bond or a triple bond would, which is to decrease the number of hydrogens you have in the molecule. So the number of hydrogens in a lookalike molecule, so that means the molecule here will be the number of carbons times 2 plus the number of nitrogens. And then you find, sorry, the number of carbons times 2 plus the number of nitrogens. And finally, you plus another 2. So why is this the case? And how do we know what are the coefficients that we multiply the number of atoms by? Well, an easy way to think of this is that the coefficient equals to the number of bonds the uncharged element forms minus 2. So in the case of carbon, carbon forms 4 bonds usually. And when you take 4 minus 2, you get 2. So the coefficient for carbon here is 2. Then for nitrogen, an uncharged nitrogen atom forms 3 bonds. So 3 bonds, so 3 minus 2 equals to 1. So this nitrogen will be multiplied by 1. You might ask, where does the final plus 2 here come from? Well, the plus 2 term arises from the terminal atoms. So in this case, we see that each carbon will be connected to 2 other atoms in a chain. So in this, sorry, it will be connected to 4 other atoms when 2 of them contribute to the chain. So for example, let's look at this carbon icircle. So it's connected to one nitrogen and another carbon, and these two contribute to the chain. Then it will be connected to 2 hydrogens. So that's why we times the carbon by 2, because each carbon will be connected to 2 hydrogens if they are not at the terminals of the chain. So for example, these are considered the terminals of the chain. And yeah, and these are the special cases we'll talk about later. So for each of these carbons in a chain, they will be connected to 2 other hydrogen atoms. Then you might ask, what about this carbon? This carbon appears to be only connected to 1 hydrogen only. Well, because this is because of branching. So instead of being connected to 2 other atoms, 2 other atoms in the chain only, it's connected to a third carbon. And because of this, you can take the final hydrogen in this branch chain and you move it here. Well, you just move it here in a head, and then this final carbon here will be connected to 2 hydrogens as well. So we don't consider this carbon as terminal anymore. Instead, we consider this carbon as terminal. So again, there will only be 2 terminals of any unsaturated molecule like this. The first one is here, the second one is here, because for the second one is here, sorry. So for this carbon, again, you only see it being connected to one other hydrogen. Well, you just move the hydrogen here at the supposedly terminal carbon of this chain, then you just count the hydrogen as part of this carbon. So this carbon will be connected to 2 other hydrogens as well. So again, you see that this molecule only has 2 terminals. So the 2 terminals here account for the plus 2 here. If this is a bit hard to understand, well, you can just memorize the formula. So an example of this is, let's say we have this formula, C4H6 ONF. So the number of hydrogens in a lookalike molecule would just be equals to the number of carbons, which is 4, times 2, and then you plus 1 because of you have 1 nitrogen. So you have 9 hydrogens in a lookalike molecule. And the number of hydrogens and halogens in this formula is seven. So you have six hydrogens and one fluorine. So in total, you have seven atoms of hydrogen and halogens. So the degree of unsaturation will just be equal to 9 minus 7 divided by 2, and then they will give you 1. So you will have one double bond or one ring. So another thing that you might ask is why do we divide the difference between the number of hydrogens in a lookalike saturated molecule without rings minus the number of hydrogen and halogen in this molecule? Why do we divide it by 2? Well, let me demonstrate with this example again. So in this case, if you form a ring by closing this, you are removing two hydrogens from here, from this carbon and this carbon. So it's minus 2. So with every two hydrogens that you remove, or every two hydrogens that's different between this and this, you form 1 degree of unsaturation. So for example, by adding this double bond, we are removing one hydrogen from here and one hydrogen from here. So to account for this double bond, we are taking a different number, like the difference in the number of hydrogens divided by 2. So one double bond corresponds to two hydrogens or halogens, because halogens also form one bond only. So in this case of a triple bond, you are effectively removing four hydrogens from this part of the molecule. And therefore, 4 divided by 2 is 2. So you have two pi bonds. And two pi bonds gives rise to a triple bond or two double bonds. So you have to really look at the formula carefully, and when drawing the isomers, if you have if you have a case with a triple bond, then you probably have another case with two double bonds. So you need to really account for all the cases, and that's why you should draw the skeletons first, and then you move the double bonds or the triple bonds. Um, you move it around a molecule to draw the different isomers, and then finally you check for duplicates. Okay, let's move on to, oh, okay. So let me just explain the case from just now, the C4H8 case. In this case, the degree of unsaturation is 1, so you can have only one ring or one double bond. So you can't draw a case with both a ring and a double bond, because that will give rise to 2 degrees of unsaturation, which your formula doesn't allow. Okay, now let's move on to talk about stereoisomers. So the first type of stereoisomers is called cis-trans isomers. So these isomers arise out of a CC double bond with two different groups attached to each carbon. So this is because CC double bonds cannot rotate like CC single bonds, because for example, if you have one chopstick, you can just rotate it 360 degrees around its center, around like the axis going through its center, and then it will still look the same because you can just rotate the chopstick infinitely. Let me just draw it here. So for example, you have a chopstick, you can rotate it this way infinitely. But if you have two chopsticks, and if you're holding on to both sides, so for example, if you hold on to both sides with your hand, you realize that you cannot really turn the chopsticks anymore. However, if you hold on to a single chopstick, then you can still turn it. So yeah, so if you hold on to one end of this chopstick, then you try to turn the other end, yeah, the chopstick will just snap, which is not allowed. So if you have a single chopstick, you hold on to one end, you can still turn the other end. So that's just a visual representation of why you can rotate a single bond but not a double bond. Okay, so in this case, I have several examples here. So for here, in this case, you can easily rotate the single bond to give you the molecule on the right. So these two are not cis-trans isomers. Whereas in this case, you cannot rotate here because it's a double bond. So the two molecules actually look different in two-dimensional space, no matter how you rotate the entire molecule. So these two are considered cis-trans isomers. Now, another type of stereoisomers that we usually deal with in organic chemistry are called enantiomers, diastereomers, and the final methyl compounds. They're not stereoisomers, but I will just put it here because all three of them arise out of chiral centers. So chiral centers are carbons with four different groups attached to it, and chiral molecules are molecules which are not superimposable, which is identical through bond or molecule rotation with its mirror image. So a pair of chiral stereoisomers can be either in, a pair of enantiomers, which is a pair of mirrored images, or diastereomers, which is a non-mirrored pair that are not superimposable. And finally, you can have methyl compounds. So they have chiral centers but are achiral. So their mirror images are superimposable upon each other without without having to break any of the bonds. So they're superimposable upon each other through single bond rotation or rotation. Okay, so I understand that these concepts might sound huge right now, but we're going to demonstrate them soon with some examples, so don't worry about that. So the first thing I want to talk about is what do you call chiral centers? So chiral centers are carbons with four different groups attached to it. So for example, this is a chiral center, this carbon here. So we usually label them with this symbol. So four groups are chlorine, then here you have a methyl group, here you have another group, and then the fourth group is your hydrogen. So these four groups are different, and that's why this carbon is chiral. So in this molecule, there's another chiral carbon, which is here. You can again label it with this symbol. It's a bit hard for me to draw here. So this carbon is chiral as well because it's attached to four different groups. So this molecule has two chiral centers. We will talk about enantiomers, diastereomers, and methyl compounds in more detail later. But first, we're going to focus on something we call priority of substituents. This will help us name the compounds better, as well as really convince ourselves whether they are stereoisomers. Also, another thing to note is that stereoisomers must have the same molecular formula as well as a structural formula. Because so structural formula, what I mean by structural formula is that you have the two things, the skeleton of the two molecules must look identical. So for example, although the chlorine and the methyl group here swap sides, they still look the same, like the chains still look the same. So the longest chain is this, and then you have chlorine on your on your second carbon, and that's also the case for this molecule. So the structural formula or the two-dimensional formula must look the same. Okay, now to classify the priority or sorry to label the different molecules with its stereochemical feature, we need to be clear with something called the priority of substituents. So you can check out the details here. We have a set of rules called the CIP rules that will help us assign the priority of substituents. But the key ideas are to look at the atoms directly bonded to the carbon we're interested in, and we rank these atoms where greater atomic mass means higher priority. And if you have a tie, so for example, a carbon is bonded to two other carbons, then obviously the two other carbons have the same atomic mass unless they are carbon 14. Then we look at the atoms directly bonded to these two carbons and then we compare the atomic masses. So for example, if one of these carbons is a methyl group or the other is an ethyl group, then the ethyl group has higher priority because that carbon is connected to another carbon, while the methyl group carbon is connected to three other hydrogens, and carbon wins hydrogens because carbon is heavier. So we only look at the thing that's heaviest. So if the carbon already triumphs the hydrogen, then there's no need to compare other things that the carbon is connected to. So when you have a double bond to an atom, then the atom appears in an additional time as a ghost atom that's not bonded to anything else. So, for example, when you have a carbon double bonded to another carbon, then it's in priority rule terms, then it's basically carbon bonded to an additional carbon, but that additional carbon is not bonded anywhere else. So for complicated cases, I recommend you to draw the priority tree, which I will introduce in the next slide. So tree drawing. So let's say that we are interested in this particular carbon. So it's connected to 4 different groups, 1, 2, 3, and 4. So these 4 groups are different because okay, so although these 3 are all carbons, they're actually different carbons because they're in different environments because this carbon is connected to here or this carbon is connected to here. So they're all connected to different parts. So they're not let's say 3 methyl groups. So they're different. So this carbon is chiral. But we're not going to be very concerned about chirality here because we're going to talk about how do we assign priorities. So the first thing we need to do is to label all the atoms near this carbon center that we're interested in, which I labeled with an asterisk. So we are going to number all the carbons near it. So if you find yourself running out of numbers, just continue numbering. Okay, so I have represented the carbon we're interested in this circle. So next, I am going to draw out what are the atoms around it. So you have carbon 3, carbon 2, carbon 1, as well as a hydrogen. So the hydrogen is the hydrogen that's pointing out here. So after that, you are going to see where these carbons are connected to. So here with our first level of tree drawing, we already know that we have 3 carbons and one hydrogen. And because all 3 carbons are heavier than hydrogen, the hydrogen is the least, the priority of the hydrogen is the least. So you can label it 4, number 4. So in terms of rank, its rank is the lowest. Then how do we rank the other 3 carbons? Well, we're going to see what they are connected to. So carbon 3 is connected to carbon 8, carbon 7, as well as a hydrogen that is here. So let's do the same for carbon 2 and carbon 1. So carbon 2 is connected to carbon 5, carbon 4, as well as hydrogen. Then for carbon 1, it's connected to 2 hydrogens and a carbon 10. Sorry, when I say carbon 10, I don't mean an isomer of carbon. I don't mean an isomer of carbon or I don't mean an isotope of carbon. I just mean that I have labeled it as number 10. Okay, so here you shouldn't care about the numbers after the carbon because these are just our labels of them. So these are just to help us distinguish between the carbons because after a while it will get super confusing. So in this case, we compare the heaviest of each group of 3. So the heaviest of this group of 3 is C10. The heaviest of this group of 3 is either C5 or C4. So let's just pick any. Then here, similarly, we have C8 and C7 as the heavier atoms, and then we just pick any of them. So C8. So all 3 are carbons, so we can't really compare between them. So then let's look at the second heaviest. So this one is C7, that's heaviest. C4 is the second heaviest. And here you have both are hydrogen, so you just pick one. So C7 and C4 both triumphs over hydrogen because they're both heavier, and that's why this group loses. And that's why its rank is the lowest of these 3 groups. Therefore, we can just label it as rank number 3 or priority number 3. Then, because these groups, they look identical right now, so let's just draw the tree further. So carbon 8 is connected to 3 other carbons. Carbon 7 is connected to 1 carbon and 2 hydrogens. The hydrogen is not connected anywhere else, so let's just delete it. Then C5 is connected to 3 other carbons. C4 is connected to two other carbons and 1 hydrogen. So let's look at C8 first because it's connected to 3 carbons. So this is obviously the heaviest of C8, C7, and H. I mean, sorry, the highest priority of these three. So we're going to take this and compare it against the heaviest or most prioritized group here. So here we have carbon 5 that's connected to three other carbons. So three other carbons triumphs over two carbon and one hydrogen. So when we compare these two, we don't notice a difference. But when we compare the second heaviest, which is CHH versus CCH, we find that CCH is heavier. So C4 has a higher priority than C7. And that's why C2 had a higher priority than C3. So we can label the priorities and then we will have our and then we would know the priority of all the substituents around this carbon that we are interested in, which is this carbon. I'll talk about why this is like noticing this and writing down the priorities is important later. But for now, let's just move on to the next part, which is cis-trans isomers and the easy convention. So again, cis-trans isomers arises out of restricted rotation around the CC double bond or really strained rings. So just now I didn't talk about the strained rings part, but for this part, you can't really turn this bond, even though it's a single bond, because it's so tight. The ring is so tight. Like you can try to make a rectangle with like four chopsticks, and you notice that this when you tie the four corners really tightly, this bond or this chopstick cannot rotate. If you hold one end, the other end cannot rotate. So yeah, so strained rings also gives rise to restricted rotation. So strained rings are usually three-membered or four-membered rings. So the requirement is basically the two carbons here, sorry, the two substituents here must not be the same, and the two substituents here must not be the same. So PQ are not the same, RS are not the same. Okay, so a special case that we have a name for is when two, so when P and R are hydrogens, or when P and S are hydrogens, or when Q and R are hydrogens, or when Q and S are hydrogens. So when you have one hydrogen on each end and the other two is the same. So for example, if Q and S are hydrogens and when P and R are the same, then we have a special case. So the special case is basically here. So here you have two hydrogens here and here, two hydrogens. Then you have two methyl groups here and here. So when the two methyl groups are opposite to each other, then they're called trans. And when the two methyl groups are on the same side of the CC bond, same side as in when you draw this, they're on the same side, then they are called cis. So cis means two hydrogens on the same side, trans means otherwise. Note that the rules for the cis-trans isomers still hold, which is that P and Q are not the same and R and S are not the same. So only either P or Q can be a hydrogen, and either R or S can be a hydrogen. So you can't have P equals to Q or R equals to S. So what if you have two hydrogens but not two methyl group? For example, one is methyl, one is ethyl. So what about that? Well, we have something called easy rules. So we can use back on the priority rules or tree drawing just now, and then we can label the priorities. So for example, if we have something like this, okay, I'll just use hydrogen as an example. Okay, never mind. I'll just put OH here. And let's say we have methyl group here. So I'm just putting Me as methyl and Et as ethyl. So you are going to compare this side. and this side. So you're not going to compare the two sides with each other. You're going to compare the atoms on each side or the groups on each side with each other. So in this case, methyl means carbon, right? Carbon is of a lower priority than oxygen because oxygen is heavier. So this is a higher priority and this is a lower priority. Then comparing ethyl or carbon, it starts with a carbon, right? Because this carbon is connected to another carbon here in the ethyl group. Then carbon is of a higher priority than hydrogen. So here, this is the higher priority and this is a lower priority. Then, because the higher priorities are on the same side or same side, so you assign it as Z isomer. I mean, of course, that's not where the Z letter comes from, but it's an easy way to remember. So it's on the same side. So yeah, so the two higher priorities are on the same side. So this is a Z isomer. Twice the isomer is an E isomer. So cis trans is not the same as easy. So in special cases, so cis doesn't mean E and trans doesn't mean Z. So in special cases, there are cases where the EZ is actually the opposite of cis and trans. I don't have an example right now, but if you're interested, you can definitely search for some examples because usually people would think Z means same side, right? Same side. Then it means cis, but that's not the case. Sometimes Z can be trans. Okay, so here we have some examples. So I'm just going to demonstrate one or two, and then we will leave the rest as an exercise for the reader or watcher. Okay, so here, let's take a look at the left side. Uh, Please remember that you're not comparing the left side with the right side. You're comparing between the upper side and the lower side, the left side. You're comparing these two, and you're comparing the upper and lower side of the right side. So here you have oxygen, you have carbon. So oxygen is a higher priority than carbon. So this is your higher priority. This is your lower priority. Then here you have carbon and carbon. So you can't compare. But this carbon is attached to three hydrogens, while this carbon is attached to one carbon and two hydrogens. So this is of a higher priority, and this is of a lower priority. So in this case, the higher priority groups are opposite to each other. So when we draw a line through the double bond, they are on opposite sides. So this is an E isomer because they're not on the same side. Okay, so let's take a look at this special case because just now I haven't talked about isotopes. So in this case, 81 is more than 79. So this is higher priority. Then 37 is more than 35. So this is a higher priority. Again, this is an E isomer. Okay, you can try these two. Okay, I might go through B because B, sorry, there's okay, I'll just go through B. So let's take a look at the left side. So left side, C, and this is also C. But this C is connected to three hydrogens. This C is connected to a ghost atom, two ghost nitrogens, and one real nitrogen. So this wins. So this is higher priority. Oh, this will be a good opportunity for me to talk about ghost atoms. So let's take a look at this. So if we expand this branch, it's basically carbon. So you used to have this carbon triple bonded nitrogen, but because we're assigning priorities, we can just expand this because it's a triple bond, so you have three atoms, but two of them are ghost atoms. So they are not connected to anything else. So they're connected to null things. So automatically they're not connected to anything else. However, this nitrogen is connected to back to carbon. Okay, so this is what ghost atom means. So these two are basically Basically, it stops at this level. You don't consider the next level for these because these are lower. So in terms of priority, this nitrogen has higher priority than these two nitrogens. So that's what ghost atom means. Then in this case, because this carbon is connected to three nitrogens, it doesn't matter whether they go whether they're ghost or real, but this carbon is only connected to one real nitrogen, one ghost nitrogen, and one hydrogen. So you have two nitrogen versus three nitrogen. So three nitrogen wins. So this is also a higher priority. So the two higher priority groups are on the same side. So that gives rise to a Z isomer. You might be asking, can you assign easy to this bond? I think the answer is no, because the nitrogen is only the nitrogen doesn't have another group here. So so it doesn't really make any difference. So traditionally, I don't think we can assign easy to this. Okay, you can do part D as an exercise, and you can pause the video here to try it out. But we're just going to move on to the next part first. So when we're ready, we can begin talking about enantiomers, diastereomers, and methyl compounds. So I'm going to re-emphasize on chirality here. So chiral carbons are carbons with four different groups attached to that carbon. And chiral compounds are compounds which mirror images cannot overlap or superimpose with each other. So for example, you can take out your left hand, take out your right hand. You find that they are mirror images of each other. So they cannot overlap with each other. Of course, you might think when you're clapping your hands, aren't you overlapping your hand with each other? Well, the answer is no, because although because your hand, if you imagine your hands are I don't know, you can put your hands together, like your hands can occupy the same space, right? They will still be different from each other because even though your hands are of the same shape, right? When you overlap them, like the back of your like left hand will be like the palm of your right hand, so they're not the same. So when but so basically they're not the same, and they're so your hands are chiral. Yeah. So, the presence of chiral carbons doesn't necessarily lead to a chiral compound because the compound can also be a methyl compound, which is that its mirror image is the same as itself. Yeah, so an easy way of identifying methyl compounds is to look for symmetry within that compound. So enantiomers are mirror images of each other, and diastereomers are non-mirror images of each other, but they are still stereoisomers. So diastereomers usually arise when you have like two chiral centers. So that's the most common case a diastereomer can arise out of. Okay, so let's just do an easy exercise now, which is identifying chiral centers. So remember, you must like the chiral carbon must be attached to four different groups. Is this chiral? Is this compound chiral? No. Does it have a chiral center? Also no, because this carbon is attached to four methyl groups. So similarly, if you have this terminal carbon, it's attached to three hydrogen groups of which are the same. So this compound is not chiral and it doesn't have a chiral center. How about this? Well, this carbon is chiral because it's attached to four different groups. You have an OH group, you have a propyl group, you have a ethyl group, and you have a methyl. So these four groups are different. So yes, this is a chiral carbon. So is this compound chiral? The answer is also yes, because like there's no symmetry in this molecule, so it's chiral. Okay, so is this a chiral center? The answer is no, because these two groups are the same. Okay. Is this chiral? You might think not because you don't see four groups being attached, but there's a hidden hydrogen. So yes, it's attached to four different groups. So this carbon is chiral. And the compound is chiral also. So chiral carbon doesn't mean chiral, but a chiral compound probably has, almost definitely has a chiral carbon or a chiral other atom, but we're just going to be dealing with carbon in organic chemistry mostly. So is this a chiral center? Well, you might think, well, these two look pretty similar, right? This and this. But here you have a hydrogen and you have another hydrogen, which makes it to not have four different groups. So this is also not a chiral carbon. Is this chiral? The answer is no. It's not even attached to four different groups. How can it be chiral? Is this chiral? Well, it's not attached to four different groups. Although you see the wedge and the dash, you might think it has stereoisomers, but it's attached to two groups of the same. I mean, both are methyl groups, so this is not chiral, and this is not a chiral center. Is this compound chiral or is this a chiral center? Yes, this is a chiral center because it has four different groups: one, two, three, and four. So yes, this is chiral. So this is a chiral center, and because the compound doesn't have a line of symmetry or anything similar, it's a chiral compound. So these two compounds are the same. So yes, this is also a chiral center. Okay, so I think now we have a pretty good idea of what chiral centers are. Okay, so we can label chiral centers with the RS convention. So an easy way of labeling is first you're going to identify the chiral centers, and the second thing is you need to draw the priority tree. The third step is you place priority or rank number 4 at the back. Then you draw a circle starting from group like rank number 1, passing through 2 until 3. And you see whether the circle runs clockwise or anti-clockwise. So if it's clockwise, then it's R. Then if it's anti-clockwise, it's S. An easy way of remembering this is S is sinister, so it's anti-clockwise because it wants to go anti to what you want. So it's sinister. And that's why it's called S. So what if a group like priority number 4 is at the front? So in this case, we have the hydrogen that's pointing out and it's also of the lowest priority. Well, you can still draw a circle from 1 to 2, then to 3. So in this case, it's anti-clockwise. Then you might think it's sinister, right? Because it goes against. Well, no, because right now, number 4, or this hydrogen here, is pointing out. So when you turn this thing 180 degrees around, you turn this molecule, right? So for example, you turn this molecule around, then the 4 points in and the 1 to 2 to 3 runs clockwise. So this chiral center, you can actually label it as R. So if you have a hydrogen that's pointing out instead of in, you just have to switch it around. So if it's clockwise, when the priority number 4 is at the back, then it's actually anti-clockwise. So yeah, you can just picture it in your head, and after a while it gets really easy because when you see clockwise, then 4 is at the front, then you know it's anti-clockwise and you will label it as S almost like automatically. So yeah, so a good way to really be fast at this is practice. Okay, so let's move on to some examples of assigning R and S. And oh yeah, one thing I should mention is that all chiral centers, I mean almost all can be assigned or S, even if the compound is a meso compound, as long as it has chiral centers, you can assign each of the chiral centers. So there are very, very special cases where the whether it's R or S is not that clear, but usually you don't encounter those cases in exams or Olympiads. So we won't be talking about that those in this video. Maybe I will make another video in a very distant future about that. But for now, let's just try these examples. So bromine heaviest, priority number one, chlorine second heaviest, priority number two. Then this carbon is attached to another carbon, real carbon, and another ghost carbon because of this double bond, while this carbon is only attached to one other real carbon. So in this case, this is number one. Sorry, this is number three. Well, this is number four. So we're going to place this group at the back. So when we place this group at the back, we kind of have bromine that is here. You have chlorine that's here, and you have your third priority group that's here. So going from 1 to 2 to 3, it's anti-clockwise, so it's sinister. S. Okay, and in this case, we're going to start by identifying the chiral center because here it's pretty clear that this is the chiral center. What about this case? Is this the chiral center? The answer is no, because you have two chlorines. So unless these chlorines are isotopes of each other, where it's specifically said to be different from each other, then no, this is not a chiral center. Is this a chiral center? The answer is yes, because you have four different groups, 1, 2, 3, and you have the hydrogen. So the hydrogen is number 4. So we don't need to label that because we know. So here, this carbon is attached to two chlorines, so it's priority number 2 because chlorine is the most heavy. So it's heavier, so it's 1. So this carbon is priority number 3, and hydrogen is priority number 4. So going from 1 to 2 to 3, again, it's anti-clockwise, but the hydrogen is pointing out. So when this hydrogen points in, or when you rotate this molecule so the hydrogen points in, it will actually be clockwise. So this molecule is, sorry, this chiral center is R. You can try to label the other chiral centers from part C to part F. And yeah. Maybe I will post the answer in the comments if actually you can just comment your answer down below and I will check that for you. Okay, you can pause the video here to take a look. And when you are ready, we can move on to the next part. So we will be continuing with enantiomers, diastereomers, and methyl compounds. So methyl compounds are identical to each other. So easy way to identify them is via symmetry. So here, sorry, this is not a very straight line. Okay, just imagine it passes through this carbon here. So because the molecule is symmetrical about this line, the compound is actually a methyl compound. So diastereomer, anyway, let's just take a look at enantiomers first. So enantiomers is, imagine you have a mirror here, then this is outside the mirror, then this will be in the mirror. So they're mirror images of each other, and that's why they're enantiomers. Also, they're not superimposable because imagine you shift this here, then this will be pointing out while this will be pointing in. It doesn't matter whether you rotate this compound or not. Even after rotation, the group on the left will still point out and the group on the right will still point in. So these two are not superimposable and they're mirror images, so they're enantiomers. Now for diastereomers, for this one, both are pointing out. For the one on top, both are pointing out. While for this one is out, one is in. So obviously they cannot be superimposed, but they are not mirror images also because when you have a mirror image of this, the mirror image basically looks like itself. So these two are not mirror images, but they're not superimposable also, and they are stereoisomers. We know they have the same structural formula, and yeah, they look the same in 2D. So if you remove the wedge and the dash, and just draw the 2D structure, then they look the same. So yeah, so they're diastereomers because they're non-mirror images and they cannot be superimposed. So similarly, these two are diastereomers, but you can't And similarly, these two are diastereomers and these two are diastereomers. So when we're saying enantiomers, diastereomers, and meso compounds, we're always talking about a pair of compounds. I mean meso compound, you can just call one compound meso compound. Okay, sorry, let me correct myself. So meso compounds, you can just call one molecule. So for example, if you aren't given all these, you're just given this one, yes, you can say it's a meso compound. But you can't say that this one on its own is an enantiomer if you aren't given the rest. So you must have a pair of molecules before you can call them enantiomers. You must have a pair of molecules before you can call them diastereomers. So for diastereomers and enantiomers, you must have a pair to determine their relationship. So diastereomers and enantiomers are relationships while meso compounds are an identity. Okay? Okay, so let's identify which are meso compounds. So for part B, the plane of symmetry is here through the middle. So yeah, it's meso. So you can draw its mirror image. It basically look the same as this original molecule. For part A, is it a meso compound? You might think there is a line of symmetry here, but the answer is no. There is no line of symmetry because here this one is pointing in while this one is pointing out. So there isn't a real line of symmetry and this compound is not meso. So you can draw out its mirror image and you will find that its mirror image and it cannot are not superimposable upon each other. Yeah. So okay, so you can do part C and part D on your own. So for part C, a tip I have is to rotate a single bond and you can draw out this molecule again. Just rotate a single bond so that the BR are both on the page. So and then you can compare both compounds. Okay, so let me just draw it out. So you just make sure that the BR are both pointing above, and then you figure out what the bottom groups are. So you just rotate the single bond until this conformation. Yeah. Okay, so an interesting property of enantiomers is that they have different optical activities. So enantiomers rotate plane polarized light in equal magnitude, called specific rotations, but in opposite directions. So so you might think that if R rotates, so you might think that R enantiomers like the enantiomer that is R always rotate light in let's say counterclockwise while uh S always rotate light anti-clockwise. But that is not the case. Being R or S doesn't mean that the light so R doesn't mean positive and S doesn't mean negative. Like there's no correlation. So R can be negative and S can be positive. I mean positive as in like clockwise and anti-clock and okay, so an easy way of saying this is that usually when we talk about specific rotations, there's a positive set and there's a negative set that corresponds to each of the enantiomers. So the positive set, like the rotation being positive or negative, has no correlation with the compound being R or S. So just because the polarities go anti-clockwise doesn't mean the light goes anti-clockwise. Yeah, I think that's a easy way to represent or explain the concept. So the optical purity is basically the specific rotation of the sample divided by the specific rotation of the enantiomer times 100%. So yeah, so that's how we know how much enantiomer there is as in like how pure the sample is. So when people say, oh, this sample is made up of this one enantiomer only, and then you find that the specific rotation is not the same as that enantiomers, you can just plug in the specific rotations and you can find out how pure the sample is via the optical activity. So the enantiomer excess is basically the the specific rotation of the R isomer minus the specific rotation of the S isomer, and then you divide it by this sum, and then you times 100%. So as I said, usually the question will give you whether the R gives you a positive rotation or a negative rotation. So don't assume any correlation that R is positive or R is negative. So the question will always tell you whether R is positive or whether R is negative. Okay? So yeah, so usually I don't think optical rotations come out that often during like Olympiads, but it's just a good to know. Okay, so now moving on to Newman projections. So the Newman projection is basically something that we use to look through a CC single bond, or sometimes a double bond is also okay, but usually we use it for CC single bonds. So, for example, if you have this molecule, you just look through the CC single bond, and then you draw a circle in between to represent that there's a certain depth to it, and then you place these three groups here, and you place the three groups at the back of the circle. Yeah. Okay, so what are Newman projections used for? Well, they're used for conformers. So conformers arises out of the rotation of single bonds. So single bonds can rotate and energy changes occur during rotation. And rotating single bonds cannot change stereochemistry. So the basis of all our discussion above was that rotating single bonds cannot change stereochemistry. It can change the conformation, but not the configuration. So generally, the most stable conformer can be obtained by placing bulky groups as far away from each other as possible. So um, in terms of Newman projection, when you have an eclipse formation, meaning the two H are basically on the same line, but here you draw it slightly apart to signal to the reader that there are two hydrogens there. So when they overlap with each other, this is typically very high in energy because as you know, electron groups kind of repel each other. So but a staggered conformation where the groups are as far away from each other as possible, this is more stable and of a lower energy. So usually your molecules will exist in your staggered conformation. Although yeah, bond rotations occur, and yeah, when you see bond rotations, you might see this graph where the y-axis is energy and the x-axis is the degree of rotation. So for example, the angle between these two. So yeah, so at the highest energy point is basically the eclipse formation, while the staggered conformation will fall here. Of course, when you have three different groups here. So when it's not all hydrogen, but it's three different groups, then here got three different groups, then the most stable conformation will be when you place the bulky group as far away from each other as possible. Okay, so I have reached the end of the contents for these slides, and I prepared some questions you can try out. And actually, that's all for today's video. If you want to read more about some things that I've gone through, I prepared a list of references that you can check out. Most of these are from Chemistry LibreText, which is free, and yeah, you can just play around with MoView as well and enjoy learning, I guess. Yeah, so see you in the next video.